So what I want to do with this video is to help connect the representation to the idea of developing and building the general case for this Hungry Caterpillar task. I'm going to start with the simpler case, the 1 through 10, but the same ideas are going to be completely applicable when you have the 1 through 100. The reason I want to do this is because, as we know, this idea of using representations helps to build that conceptual understanding, right? If we can draw a picture, if we can use the manipulatives to depict what's going on in the scenario, we actually understand it better. And using the representation is actually going to help us to make sense of how that we got the equation that we did and why the equation, how it works. And we're going to also see equivalence. I also want to make a note that while, yes, we created an equation and some of you called it a formula, I want to encourage us to change our language to be finding the general case. The reason that is so important is because think about SMP number 4. We were very confused about it at the beginning, but what you did, you created a mathematical model when you created that equation, right? You could generalize this situation of the caterpillar eating, one piece of fruit every day, one more for 10 days. But now with your model, you can predict, well, how many pieces of fruit will he eat on the 101st day or the 200th day or the 2000th day, right? That model, think about equation, now is SMP4. You created a mathematical model that can predict the total amount of fruit given any day that you want. So what I'm going to do is show you, a few of you created such a representation like this where one piece of fruit is at the top, then day 2 is 2, 3 pieces of fruit, 4 pieces of fruit, all the way to 10. Ones that look exactly like this with the counters, and others had used tiles. I also had the thought when I created this, wouldn't that be cool with the Cuisinart rods and to show also all the different colors. So what I want you to see, and somebody had an amazing reflection that looked like half of an array. And that's exactly how we can start to develop this idea of that general case. If we see this as half of an array, well, we can copy it using our tech tools. And note that I'm going to change the color of these counters to yellow, and I'm going to group this. We can literally create such an array. So you could do this with your counters. You can do this with your physical counters if you'd like, or same thing with the tiles. And now we see that we have 10 in the vertical column by not 10, but how many? 11, right? This is, so for so many of you that paired 10 plus 1, 9 plus 2, 8 plus 3, 7 plus 4, you see where these pairings come from now, right? This is the n plus 1. Or if you're on the 9th day, right? But then if we want to now, well, how much total is just the area, it's just the array. So now we know that the total, the height of this rectangle is n. But we know that this equation is not n plus 1 times n. I'll put it over here, but we don't need the whole thing. What do we want? We want half of it. So now we get the total number of all of the purple as this n plus 1 times n array, but we only need half of that array. So that's why it's n plus 1 times n all over 2. Another way to think about this for those that had grouped in sets of 10s was, oh, I see a group of 10 at the bottom, but what I can do, and again, I'm going to change my colors here. This time I'll use maybe a light blue. I can make these pairs. 9 plus 1 is 10. 8 plus 2 was 10. 7 plus 3 is 10. And last one, sorry. 6 plus 4 is 10. So now we see, again, we have, we see that our bottom row is n, right? There are 10. But now, what's our height? It's not 10, but 1, 2, 3, 4, 5. Half of 10, n over 2. And then, but we have this weird extra 5. People were talking about, I didn't know what to do with this piece that was left over. Well, we just add it, right? So now we can begin to see our expression. The bottom row, n, times the columns, n over 2, then plus another n over 2. How can we use our algebra skills to see how this is equivalent to the other expression? Well, we can notice that this n over 2 factor is in both of these terms, right? It's n times n over 2 plus 1 times n over 2, or just n over 2 by itself. If we divide each term by this factor of n over 2, same as factoring out this factor of NO2, and n over 2, n divided by 2, we will then be left with, in this first term, n plus, and then again divide n over 2 by n over 2, that gives us 1. If you use the distributive property and multiplied n over 2 back in here, you would see that these expressions are in fact equivalent. So that helps us to see how this representation with the counters in this case can really provide that conceptual understanding of where these n's come from, where these equations come from, and how they relate to building this idea of this general case, which is so important, again, for them not only to make the connections, because for so many these n's seem like a foreign language, but also to see that it really means any number. And I loved how you guys were able to plug in, or in this case, n is any day. Plug in the day number 100 or 2000 or 50 and made sure that the general case here that we've created worked with the calculations that you had found previously.